Give me a moment. Okay, let's get started. So, how was the midterm for you all? So, I think, like, I graded problem 2. Problem 5 was just a freebie, I think. Like, for what primes does you have a root, you just plug in 2 and then figure out, like, rent it 0. So, I mean, so unless you made an algebra error, problem 5 was like a freebie. So problem 2 was show the units are unique. So I think the common mistake was if you assume there are 2 units, assume you have like E and E prime, right? Then you know for all A and R, like A times E is E times A is A, and A times E prime, that's also A. So sorry, this, yeah, that's also A. So a lot of people just said this, right? And then they canceled, right? In other words, they just canceled and said, so this is wrong. Yeah. So like you can't cancel because the problem had no assumptions on R, right? Like a lot of people just said like, because the reason you could cancel is if you do AE minus AE prime is 0, you factor it out. And like a lot of people said, like, because this is a unit, so this is not a unit. Yeah, like E and E prime themselves are a unit, like, right? But their difference need not be a unit, right? I mean, in fact, you're trying to show they're equal, right? So if your goals are trying to show they're equal, this thing is 0. So I mean, like, the difference of 2 units need not be a unit, right? Like Z quotient for Z. 1 is a unit, 3 is a unit, but 3 minus 1 is 2 is a 0 divisor, right? So like so basically in order to cancel, right, you need to say, you need to be in an integral domain, right? And the assumption never said R was an integral domain. Sorry, take, so since it holds for all R, for all A, so people said take A, not 0, right? So fix an A that's not 0, and then so if it was not an integral domain, I mean, if it was an integral domain, this proof will work. But we there's no assumption on that. Everyone clear? Yes, no. Okay. So, okay, so we're gonna go into ideals. So I feel this is like a, you know, completely new topic. So let me remind you, an ideal is right, it's an additive ideal n of ring R. You would take n of this, not this n of ring R. So let me just say for that one, you just since you know it holds for all, for all like A, so this is for all A and R, and then you take A to be E prime. Yeah. So on one hand, E prime times E is E prime. On the other hand, since the other one's the identity, this is also E. Yeah. And then you're done. Yeah. So this thing is because E is identity. And this thing is because E prime is identity. Does that make sense? Like, so you're supposed to choose a particular element. Like it's so that the part two, if you know what to do, it's like a one-line proof. Like, there isn't really much to do. So yeah, okay. And then it's an additive subgroup, right? With like this magnet property, right? With additive subgroup with the property that AN is a subset of N. And NB is a subset of N. So we need the second one in case R is not commutative, right? But for all A, B, and R. So if R was commutative, right? NB is just BN. So you just need to check one way. Okay. So, and with this, we could take factor rings, right? So quotients, right? So let me just ask a few questions on quotients just to get people's head thinking. So example, give an example to show that a factoring of an integral domain can be a field. So what integral domain do you know such that when you quotient out by an ideal, you get a field? Yeah, Z mod 7Z, right? Good. Okay. Just to get your head to think. So how about this? Give example. I'll just use EX for example. Give example of factoring of factoring of integral domain that have zero divisors, right? So it's possible, right? When your original ring had no zero divisors, but when you quotient out by the ideal, there is zero divisors. So can anyone give me an example of that? Um, well, what rings do you what rings do you know has zero divisors? Give me one. Yeah, that's it. Yeah. So Z is an integral domain. 8Z is your ideal. And when you quotient out, it has zero divisors, right? Everyone good so far? So it kind of shows factor rings are, you know, different from like it can be different from the original. Okay, so with that in mind, right, we know every ring R has at least two ideals, right? The whole ring is an ideal, right? So we call this, I think the book calls this the improper ideal. And you always just have to set 0, right? This is the trivial ideal. Yeah. And if you remember, what rings only have these ideals? Well, they're fields, right? Fields only have these 2 ideals because anything else is a unit. And once you have the element 1, you have the whole ring. Okay, everyone clear so far on like definition of ideals? So now we're gonna go into types of ideals, and I'll sort of explain why they're important. So the whole crux of the matter is maximal / prime ideals. So what is a maximal ideal? It's exactly what you think, right? Maximal ideal of a ring R is an ideal M different from R such that there are no, sort of what you think, right? It's the maximal one. So there are no proper ideal N of R properly containing M. Containing M. So of course, M is contained in R, right? I mean, R is the whole ring. If your ideal is always containing your whole ring, but maximal just means there's no bigger ideal that's not R, right? That contains M, right? So it can't be contained in some bigger ideal. That's what we mean by maximal. Yeah. So let me just give an example. Let me ask a question. Like take R to equal Z. Is M equals 8Z a maximal ideal of Z? I mean, using this definition. So can you contain 8Z in another ideal? Think about it. So is there some bigger ideal that's not Z, the whole ring itself, that contains 8Z? Yeah, 4Z, right? Like 2Z, 2Z, 4Z, like see? So you can see that 4Z is also not maximal, right? It's contained by 2Z, right? So no, right? Because 8Z is contained in 4Z, right? Like these are all multiples of 8. These are all multiples of 4. Everyone clear on this? Yeah. Okay. So, but obviously, we don't want to, these are, integers we know nicely, right? But given a ring, we want to, we don't want to try to, just cook up an ideal, right? Because what if like I did give you a maximal, right? One, right? Then like you're not gonna, people who spend time trying to cook up something bigger are just gonna fail, right? Because it was maximal, right? So you don't want to just keep trying to look for stuff. You want like a valid way to show something's maximal. And there's a theorem that says let R be a commutative ring. So this is like the crux theorem. So commutative ring with unity, then M is a maximal ideal of R. Let me just say of R. If and only if R quotient M is a field. So this is why I'm asking you, you need to understand quotients, right? So in the example before, right, 8z was not maximal ideal of z because z quotient 8z is not a field, right? So can anyone give me an ideal that is maximal using this theorem? Yeah, so 7z is maximal, right? Because z quotient 7z is a field. So let me be careful here. Right? When we say maximal, maximal is different from maximum, right? Maximum is like biggest, and that need not exist. But like maximal means it's biggest amongst those that can be compared, right? Like you see that there could be more. See, if it's maximum, normally like you only think of like one maximum, right? Unless, but like there could be lots of maximals, right? Because 2z is maximal. Because z quotient 2z is a field. 3z is maximal, right? So it's for those that can be compared, right? Because like 8z was contained in 4z, which is contained in 2z, right? But like you can't compare like 2z and 3z, right? They're not like fully subsets of each other, right? So like you can only compare those that are like fully kind of like full subsets of each other, right? Like these you can't compare them because none of this, neither are true, right? So think of maximal as like maximum amongst those you could compare via subsets. Yeah, is that clear? I don't know how to explain it better, but uh, okay. So yeah, good. So i.e. Z mod PZ is a field. So PZ maximal ideal of Z. Okay. So with that in mind, right? Um, now let's go to a prime ideal, yeah? And you'll see the analogous thing. So prime ideal. An ideal n not equal to r is prime ideal of r if for all a b in n implies if if what this yeah, if for all a b in n a is in n or b is in n. Yeah, so whenever you have a product of two elements in r that is in n, one of them has to be in n. Yeah, it doesn't need to be both, just one of them. So right, so let me just say, right, how do you determine this? It's a similar theorem, right? Let R be commutative ring with unity, because you don't want to check every product, right? That's impossible. If your ring is infinite, like you're not going to check if every product belongs to n, one of them belongs to n, right? That'll take forever. So commutative ring with unity, um, um, n not equal to r. Ideal of r, then r mod n is integral domain. So now we're using all the definitions you've learned before. So the quotient is integral domain if and only if n is prime ideal. So can anyone give me a quick proof of why maximal ideals are prime. Okay, in commutative ring, in our commutative ring with unit. Yeah. It's so when are you maximal? N is maximal. Let N be maximal, right? Then you know R mod N is a field. But fields are integral domains, right? So R mod N is integral domain. Right? So N is prime. Everyone clear so far? At least a quick proof. So this isn't a priori intuitive, right? But if you assume the two theorems, this is trivial. So instead, how about this? Since let's just practice definitions of maximal ideal, right? And ideal. So I'm gonna, not use the theorems and try and just prove this directly, right? So let n be maximal. So let me just say longer proof, yeah. So longer proof, right? So we're gonna prove maximal ideals are prime. Yeah, so we're gonna practice using the definitions, right? So we're gonna do contradiction by contradiction. So let M be maximal ideal of R, right? Assume there exists A, B, and R such that the product is an M, but A is not an M, B is not an M.
Call from
So can anyone tell me what's the next step? So how about this? What can you all tell me? Is this an ideal? Is AR the set of AR such that R is an R? And BR is a set of BR such that R is an R. Is this an ideal? Let's practice definitions here. Is it an additive subgroup? So AR1 plus AR2 is certainly close under addition, right? Because this is a ring, so this is still A times something in R by distributive property. And since R is a commutative ring with unity, well, if I multiply by some R prime AR, well, I could commute and say this is R prime R. And now this is just some element in R, right? So this is again an element in AR. So we have the magnet property. So is everyone clear that these two are ideals? Yes or no? Okay, and do you all remember given ideal, I did this before, given ideal IJ, I plus J is an ideal. Yeah, if you, so this is the set of I plus J such that I is in I, J is in J. Do you all remember this, or do you need me to just quickly convince you? Okay, so can you tell me about this? So and let me just say, I plus J contains I, and it also contains J, right? This is a bigger ideal. Do you all agree? Because here I could take J to be 0, then I plus 0 is I for all, and then so we contain every element in I. And next, similarly, I could take I to be 0, and then I contain every element in J, right? So 0 plus J is J. So is everyone convinced that like the sum ideal contains the original two? Okay, so what I'm gonna do is hopefully you all see it. I'm gonna add it to M. Yeah, this is the sum of two ideals. It's an ideal. What must this be? This contains M, but M is maximal. So what must AR plus M be? So let me go back. So here, right? If an maximal ideal cannot be, it's a proper it's a ideal different from R, right? So yeah, you're right. So from what you said, right, it must either be M or the whole space R. Do you agree? You can't have anything in between because M is maximal. Does everyone see this? Yes or no? So R plus M is equal to M or R. Yeah, we're gonna derive contradiction. I'm just saying, right? For now, it's M or R, right? But we know it. So if it was M, if one of them was M, then we are done because like this has 0, and AR certainly AR contains A, right? Because A times 1 is A, but that would mean A plus 0 is an M, right? And that's a contradiction because we assumed A was not an M, right? So it can't be this case, right? So we're going to show it can't be all the cases, and then we get a contradiction. So by same argument, it can't be M here, right? Or else we would contain B. Does everyone see this? Because A plus 0 is A. Yeah. So the only case is if they are both R. Is everyone clear on this? Does everyone follow? I'm just doing this proof so we all get used to the definitions. Yeah. You could certainly use the theorem, but I figured it's since ideals are still new, you know. Okay, so AR plus M is R, BR plus M is R. But R contains 1, right? So there exists R1, R2, right? Because they're equal, right? There's some combinations. There's the AR1 plus, I'll just say M1, so M1, M2 is equal to 1, and BR2 plus M2 is equal to 1. Everyone follow? So, I mean, they're equal, right? So so there must be some element such that I get 1 because 1 is an R. This is plus, by the way. Do you all follow? Yes? No? This is by definition of these being equal. I mean, if 1 is an R, right, then there must be some combination here that gives 1. So I'm saying it's just say it's AR1 plus M1, right? 1 is an R here, so there's some combination here in this set that gives 1, right? I mean, because the sets are equal. Okay, now we're done because BR2 plus M2 is 1 times 1. So it's just, 1 times 1 is this. Then ABR1, I'm bad at foiling. AR1 M2 plus BR2 M1 plus M1 M2. Yeah, so this is equal to 1. Yeah. But now we're done because we assumed AB was in M, right? So this whole thing is in M by magnet property. Yeah. Similarly, M2 is in M. So this whole thing is in M by magnet property, right? M1 is in M. So this whole thing is in M by magnet property. M2 is in M. So this whole thing is in M by magnet property. So, and M is an additive subgroup, right? So this means the whole left-hand side is an M. Do you all agree? But that means 1 is an M because they're equal. And what do you know about an ideal that contains 1? What must it be? The whole ring. And that's a contradiction, right? Because we assume that maximal ideals, it's different from the whole ring. Yeah. So that's like the straightforward proof that maximal ideals are prime. So we actually use the whole everything we've learned pretty much for this proof. But yeah. So is everyone clear on definitions? At least they're more comfortable with the definition of like maximal and prime. Yes, no. Okay. But you don't have to do this. You can just use the theorem. Yeah. Hey, the theorem is there for you, but okay. Let's continue. So let's do examples now, yeah? I don't want to go too far ahead. So we're gonna just practice examples of prime maximal stuff. So find all C in Z mod 3Z such that. So this is just practicing, quotients, yeah? Z quotient 3, Z of X, quotient X squared plus C is a field. Right? So let me do the first one. Is this a field? Is everyone clear what I mean by X squared parentheses? So this is X, by this, I mean this. So it's the set of X squared times F of X such that F of X is in Z mod 3Z of X. Yeah. Right. So like, is what I wrote before, like AR is the set of A times R such that R is an R. It's the exact same thing. It's except in this case, R is this thing. Yeah. So, and we normally write functions as F of X. So I just write F of X. Yeah. So it's nothing new. Yeah. So is this a field? So how about this? Use what we just learned, right? If it was a field, what must X squared be? What type of ideal must X squared be? Maximal. Good. Now, is this maximal? Can you think of a different ideal that's bigger, that's not the whole ring, that contains this thing? sorry, this thing. Yeah. Yeah, X, right? This certainly contains the top one. Do you all agree? So one way to go about it is say this thing is not maximal. It's contained here, and this thing isn't the whole ring, right? Because there's no constant term, right? These are functions without constant term. And most certainly the ring here has functions with constant terms. So you already know this is not a field, right? Oh, sorry. Um this is the wrong question. But uh that yeah, sorry. So this is just is this a field? Yeah. Maybe that was why you were all confused. But here, it's easier, right? So, or you could work with the quotient. So you could go both ways. If you don't like this way, then what is x squared in this ring? In the quotient, what is x squared? If I'm modding out by x squared, what is x squared? Yeah, it's 0, right? I mean, kind of like this, right? If I mod out by 3z, what is 3? It's 0, right? Basically everything in 3z. What does it mean by quotienting? It means everything in 3z is 0, right? It's the identity now, right? So same thing here. Everything in here becomes 0. So x squared is 0, right? X squared is 0 in the quotient. Everyone agree? Yes? No? So is this clear? Okay, but then that means we have 0 divisors, right? Because x times x is x squared, which is 0. But this is not, none of this is 0, right? So x is a 0 divisor. And question, can a field have 0 divisors? No. So here's another proof that this can't be a field, because this ring has 0 divisors. Yeah, so you could work with the quotient, or you could work with the ideal, whichever is more comfortable for you. Yeah. Everyone clear on this? So I'm gonna change the question a bit. What about x squared plus 2? So again, this is again, it's shorthand for this, right? Is this maximal? So let me give you a hint. Yeah, in general, it's a field if something is irreducible. Yeah, if the thing is reducible, it cannot be a field. Like this thing, the thing we did before, this thing's reducible, right? It factors as x times x. You all see this? And if it factors, well, this ideal is bigger. That's how you get the x here, right? So here, right, it's the same thing, right? What is x squared plus 2 in z mod 3z? Well, 2 is the same as 1, right? So is everyone clear that these two are the same? Because 2 is just 1 in z quotient 3z, right? Everyone agree? So what does this factor as? X squared minus 1 factors as x minus 1, x plus 1, right? So what you're going to see is it's contained in this ideal. It's contained in the ideal x minus 1 such that f of x, times f of x. So you see that this cannot be a field because this thing is a bigger ideal, right? So, and then again, if you want to work in quotient rings, well, I know x squared plus 2 is 0. Well, I have 0 divisors because x minus 1, x plus 1 is x squared plus 2. But this is 0. And none of these are 0. So can't be field again because quotient has 0 divisors. So you see in this case, it's not even prime, right? It's not even a prime ideal because the quotient is not an integral domain, right? So, like this ideal is not prime and it's not maximal, right? So everyone clear on this? So that's why you learn irreducible, right? Because these things are reducible. So when you quotient out, bad things happen. But so let me convince you, right? Let's do something that's irreducible. So x squared plus 1. So this thing over z3 has no roots, right? 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5, but 5 mod 3 is 2, yeah? So this thing certainly is irreducible. Does everyone agree? Okay, so, in here you could play around with it, right? So again, does everyone agree that in this case, x squared plus 1 is 0 in quotient? Everyone agree with this? Then what is x squared? X squared is the class of x squared is just the class of minus 1, right? In quotient. So the claim is all represented classes in quotient group can be represented by linear or constant terms. You can't have anything more. So let me just, without proving, convince you, right? If I had like x to the 5th plus 3x cubed plus 5x squared plus x plus 1 in the quotient, this is in quotient, I can make this linear or constant. How? Well, what's x squared? X squared is -1, right? Do you all see this? So this is just -5. What is this? Well, this is 3 times x squared. So this is -3x. Agree? Because x squared is -1. This is x squared times x. This is -1. This is -1. So this is just x. And then x plus -3x plus x is just -x, right? And then -5 plus 1 is -4. And -4 is what? Mod 3. It's 2. I mean, if you like positive things, -1 is also 2. So it's just this element, right? So the class of x to the 5th plus 3x cubed plus 5x squared plus x plus 1 is just the class of 2x plus 2. Is everyone clear on this? Yes? No? Did I convince you all? I mean, it's the same thing here, right? If I take any element in Z, I can reduce it to either the class of 0, 1, or 2, right? Like if I take like 500, like I know 3 is 0. So this is just it's the same thing as what I did right here, right? 500 is 3 plus 3 plus 3, you know, however many times, and then whatever remains is your thing, right? I mean, in this case, what is it? If you like, it's 3 is 0. So what is this? 1, 26, 18, 20. So this is 3 times 166 plus 2. Yeah. But 3 is 0. So this thing goes away. And then it's just 2, right? Same thing here. All right. I take an arbitrary element in here. Let's just, I mean, I just made this polynomial up, and then you just keep reducing. It's the same idea, right? Except an arbitrary element is an arbitrary element here is an element of Z, right? It's a number, right? An arbitrary element here it's just a polynomial. Everyone clear on this? I mean, you've done this before in like, Z mod NZ. It's just that your ring's different now. Okay, so now we have elements. So all elements are of the form ax plus b, right? So we have 2x plus 1, 2x plus 2, 2x, right? X plus 1, x plus 2, x, and then 0, 1, 2, right? For example. All right, these are all the possible linear terms, right? Because we're in Z mod 3Z. And you could check every element here aside 0 is invertible, right? Let me just convince you. X plus 1 times x plus 2, these are inverses. Why? Because this is x squared plus 2x plus x plus 2. This is 3x, right? 3x in 3 in Z mod 3Z is 0. So that goes away. X squared is -1, right? So -1 plus 2. Indeed, it's 1. Yeah. So these are inverses, right? So you have, what's the inverse of x? Well, let's multiply by 2x. That's 2x squared. What is x squared? X squared is -1. So this is -2. And then if I add 3, right? -2 mod 3 is just 1 mod 3. And you could check for the other elements. I'll let you have fun with that. But this is a field, so you could show every element has an inverse. Is everyone clear on this? I think that's a lot for today, but hopefully I convince you this quotient is a field. Good, yes, no. Yeah, it's because x squared plus 1 is irreducible. Yeah. But I mean that's something you'll learn later. I just wanted to give you a heads up. That's the reason. But don't use that yet. So don't just write in your homework like this is a field because this is irreducible. To show it's a field, right now, there's only finitely many elements, right? So find the inverse to each. I found you the inverse. These two are the inverse of x plus 2 is x plus 1. Right? The inverse of x is 2x, right? So just write out all the inverses. Good. Okay. I'll stop sharing.